Well, welcome to physics class. I am excited about physics. It's the one science class I teach, and a lot of what you're going to discover is it's going to feel a lot like a math class. Okay, so Kendall, you missing my pre-cal this year, but you'll at least get physics, so you get a little bit of dose of math. One of the things I love about physics is twofold. One, you always hear growing up, at least I remember this growing up in junior high, math is the language of science. And there was never any math. Now, you got blindsided by physical science, right, in 9th or 10th grade, and it's like, math? I remember my 9th grader saying, do we need a calculator for this class? I'm like, no, you need the calculator for physical science. What? So they're going to find out what you found out. But all of a sudden there's math. And in chemistry, there was definitely some math, right? So physics continues that. Another thing I love about physics is, all through Algebra 1, so when am I ever going to use this? What's the point of this? Physics is the point of this, and to a small extent, I would say chemistry as well. You use some algebra for sure in chemistry, but physics to a greater extent. And it's where all of this algebra comes around again, like, oh, that's why I learned how to do this, that, and the other in algebra class, was so I could do physics. And so physics really ties math in with science in a great way. The other thing I love about physics, more so than chemistry, and I'm not trying to hate on chemistry class or anything, is chemistry, like you do get to burn stuff, hair, whatever. And I enjoyed, I don't think you all got to do it, the flame tests, where you burn different chemicals and they burn different colors. I thought that was super cool, especially when you're like, oh, this is how they make fireworks, different colors. They put different chemicals in there and explode them, and it's great. Nashville is, I think, some of the best fireworks I've ever seen. Better than the DC fireworks. Nashville fireworks are pretty awesome, so I've watched those the last couple of years, since Columbus and Phoenix City have been subpar at best, or not doing them at all in some cases. But anyway, chemistry's got some cool aspects to it, but a lot of what chemistry is at a level you can't see. Like, it's at the molecular level where there's this ionic bonding and you can't even see what's going on. You know it is. Physics, everything we're going to talk about pretty much, you're going to be able to see. What it's going to do is it's going to help you understand, oh, this is how this works. This is why this works. And it'll make you feel like a nerd, because something will happen, you're like, oh, I know why that happened. And I have to say, as a physics teacher, it makes me feel even more like a nerd than I was already, because everything, oh, I know why that happened. And, oh, see, you can explain that through this and different cool stuff. Mr. McDonald was complaining about his coffee yesterday. It's too hot. And he's like, I'm waiting for it to cool down so I can drink it. You don't want to put ice cubes in, though, because it dilutes the coffee, right? And coffee drinkers? You're with me. Coffee's too bitter. It doesn't taste good. Forget the coffee. They like the coffee. But you don't want to put ice cubes in the coffee because it waters it down. And you could, if you were really hardcore, freeze coffee, right? So you would drop coffee cubes instead of ice cubes so it can cool the coffee if you wanted to drink it quicker. Or just wait it out. And so, actually, on Shark Tank, there was this product called the Julie. This is apparently a pitch for them. I've actually never bought it, so I don't know how well they work, but supposedly, drop them in the coffee, and they absorb the thermal energy from the coffee, get the coffee down to the appropriate temperature, and then slowly they maintain thermal equilibrium, release thermal energy back into the coffee to keep it at that drinkable temperature. And they designed them with this supposed, whatever the perfect coffee temperature is, they figured it out, and that's what the Julies are supposed to get the coffee to and keep it there for like 6 hours. And they're washable, reusable cubes made of some substance, some chemical substance that does that. Well, that's science in action, right? But there's this, and it's, thermal energy being sucked out. You shake hands with somebody, their hands feel cold. Why? Okay, we answer those questions, You try to round a corner, and it rounds funny. You're like, why? All kinds of things we're going to talk about this year that after we talk about them, it's just going to kind of open your eyes to the wow, the why that we're going through this year. So I love teaching physics. I will admit, in high school, I didn't appreciate it like I should have. I was a senior like you, and I was more focused on sports, and so I got through it okay. And my physics teacher got mad at me a few times because I wasn't applying myself like I should have. College physics, I was tired. My class at both semesters fell after lunch. Tired. I had a girlfriend, would rather spend time with her than think about physics. And so really didn't appreciate it like I should. And my second year teaching here, we needed an extra science elective. And I'm like, they really need physics. I'm the only one here qualified to teach it. I'll suck it up and teach physics. And that first year teaching it, man, I was doing a lot of research because I hadn't applied myself like I was supposed to in high school and college. And all of a sudden, it became, as I prepped more, I began to understand, I was like, wow, this is actually really cool. I should have paid better attention earlier. And my high school and college physics teachers were gracious and they helped me out with stuff. But I really began to appreciate it. Every year I teach it, just more and more. New stuff that I see and understand and get to share. I think it's really cool. So I say this about a lot of my classes. This may be one of my favorite classes to teach because it really becomes really hands-on and practical. And so I love that. But what is physics? If you get this definition down, we'll start here with your first definition for physics, the title of the class. We should know what we're studying here. Physics studies the interactions between matter and energy. What you studied in chemistry all of last year was the composition of matter, changes in the states of matter. Here we're going to relate matter and energy together. And that's really what we're studying here in physics. The branch of science that deals with the interactions between matter and energy. You see that on page 2 if you open up your textbooks. Page number 2, they list different branches of science. Some of these you've studied, some of them you haven't. Astronomy, it'd be really cool if we could make that its own separate class. You got a tiny bit of astronomy in junior high science. Biology, spent a whole year studying living things. Chemistry last year, changes in matter. Geology, a little of that was in junior high science. Physics, matter and energy, that's what we're studying. Interactions between matter and energy. So largely what we're going to talk about this school year then in physics, we're going to start by focusing on matter. Almost all of it will be review because you studied matter in great depth in chemistry last year. So we're going to review over matter, all the basics. We'll take a few different twists, do a few different approaches that maybe you didn't look at last year. And then we'll turn the page and we'll go to, okay, now let's talk about energy. Let's talk about movement and different things like that. And so get into that in great depth. Why? Why study physics though? Why study science in general? A couple of reasons for you. First of all, God commanded us to have dominion, right? The command started with Adam, it carries down throughout, to have dominion over creation. And that doesn't mean we abuse creation. We're like, a tree, let me chop it down and burn it because I can, I'm a man, I have dominion. No, it means using, right, what God has for us. Here's my definition of dominion as far as in the sense of having dominion over God's creation. Dominion is using the resources of nature and applying laws of nature. Using the resources of nature and applying the laws of nature to better ourselves. I'm thankful for air conditioning. Somebody figured out that just the right chemical, usually Freon, and forced air through a certain way, and you can suck energy out, and that makes air colder, and you can blow cold air through something, and it cools the air down. It's great. Refrigerators are wonderful. Glad we don't have ice boxes. We're constantly changing out blocks of ice or having to salt our meat to keep it from going bad. Now, that was science in itself, wasn't it? People figuring that out. But I'm glad we've made advances. Makes our lives more comfortable. They've discovered certain materials are better for this, that, and the other. Glad they discovered aluminum. Didn't rust. Make things out of aluminum so you don't have rusty this, rusty that in some cases. Galvanized steel, more resistant to corrosion, all kinds of different scientific advances, and applying different laws to better ourselves, using the resources God's given us to better ourselves. That's one reason why we study science. Now, we're not going to be breaking a whole lot of new ground, but you can't break new ground without knowing ground that's already been broken. So I'm sharing with you as the ground that's been broken, and then if the Lord leads you into the field like this, then you can go break new ground yourself. Another big reason, and this is going to be an emphasis in the class, is seeing the handiwork of God. We want to see God's handiwork in creation. It amazes me the idea of an atheist. An atheist is anti-science. An atheist, or perhaps one who's just ignorant of science. Because when you study science, especially in physics, as we begin to see the mathematical orderliness of everything, everything comes down to equations. Everything comes down to a mathematical orderliness. Even if you don't want to accept who the true God is, you have to admit there is at least some higher power, some supreme being, some intelligent designer to all of this. There's no way this could happen mathematically by chance. It takes a lot of refusal to accept science or learn science to be an atheist. Now again, that may or may not get you to knowledge of the true God, but at least looking around at the universe, understanding how everything works, will solidify in your mind, there has to be a God. We call this general revelation, if you write that term in your notes. General revelation. General revelation is God's revealing of himself through nature. God's revealing of himself through his creation. We look around at the world and we see the orderliness. We realize how everything runs according to mathematical principles, and we realize there has got to be someone bigger than I who made all of this happen. It could not have happened by chance. You don't get order from disorder. This happened on purpose. Now, does that necessarily tell you who the true God is? No, it can reveal a lot about God. You look at the beauty of God's creation, until man messes it up. You look at the beauty of God's creation. Man, this must be a good God, a loving God, to give us all this, to have made this planet so perfectly habitable for humans. I mean, this must be a good God, right? But it doesn't tell you who the true God is. That takes the Word of God, and that's why God gave us the Bible. Special revelation is the term for God's Word. Special revelation is how we can refer to God's Word. And that tells us specifically who God is. It's Jesus Christ. And the Bible tells us that. General revelation tells us there is a God, and we can learn some things about God, his power, his awesome power, the immensity of God and his knowledge. We study the immensity of the universe in astronomy. You study the intricacy of the human cell in biology. To see the incredible wisdom of this God, but to know who God really is, it takes special revelation, and that is the Bible. Interesting verse, you see it on page 3, it's in italics there toward the bottom of the first paragraph, Romans 1:20. Kendall, would you read that verse for us? Very bottom of the first column.
For the invisible things of him from the creation of the world are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that they are without excuse.
The Bible says here, although we cannot see God, God is a spirit, although we cannot see God yet, when we get to heaven we will, we can understand who he is in a large sense from the things that are made, right? And the Bible says that those who reject the idea of a God are without excuse, for God's revealed to them that he exists. Again, I also believe, God says in another passage of Scripture, that those who seek me early shall be found of me. I'll be found of them that seek me, right? So that people in a part of the world that don't have the gospel, if they seek after God, if they seek the light, God will give them more light. This is one reason why it's important to surrender to what God has for us, right? God pricks on your heart to go somewhere as a missionary. It's important that you go because it's very possible there's someone there who's seeking God, and God wants to use you to be that light. Now, if you won't, God will find someone else. But wouldn't it be awesome to be that light? You hear stories of missionaries who go to this part of Africa, for instance, and the people there, I was praying, wondering, God, whoever you are, would you reveal yourself? And now you show up. And the missionary's like, wow, that's really cool how God works, And it is. It's true. God works in great ways. Wouldn't it be great to be part of that? Also, as we study creation, as we study science, right, there's the philosophy of atheism. There is no God. This all just sort of happened, right? Or evolution, which comes from atheism. It all just happened by chance. And everything just somehow came into order and becomes better and better. And now here we are, man, the zenith of evolution. Oh, there's another verse that speaks to that, and certainly this agrees with the laws of thermodynamics, middle of the second column, from Psalm 102. And Michael, if you'll read those verses for us.
Did you say Psalm? Oh, okay. Of old hast thou laid the foundations of the earth, and the heavens are the work of thy hands. They shall perish, but thou shalt endure. Yea, all of them shall wax old like a garment. As a vesture shalt thou change them, and they shall be changed.
Everything's running down. Everything's going to be destroyed, but everything's running down. God laid the foundations of the world. God created it. And little by little, it's wasting away, deteriorating, as the laws of thermodynamics say. And one day, God will make all things new, right? Well, again, that flies in the face of evolution, but so does science, right? So science flies in the face of evolution as well. So there's some reasons why we want to study science in the first place. This would be true for all the science classes, but of course true for physics as well. We want to learn as much as we can so we can have dominion over nature, so we can use it to better ourselves, responsibly, of course, and then so we can see God's handiwork and really understand more about this great God who made all things. Well, there's a couple branches of physics we could break physics into. We have classical physics, first of all. Classical physics refers to the areas of physics that have been studied from the Protestant Reformation on to the 1900s. Now, I think it's interesting, first of all, that the Protestant Reformation is where it all started. Right? The Renaissance, the Protestant Reformation kind of went hand in hand, didn't they? Prior to the Protestant Reformation, little history question, what did we refer to that period of time before that? Do you remember? From about 500 to about 1500, about 1,000-year period of time, called the medieval period or the Dark Ages, was the term used for it. The Dark Ages. No new discoveries, no new advancements. Why? Man had really kind of stepped away from God. Why would I study about creation if there's not really a God to know? But it was amazing, around the 1500s, when Martin Luther just started the Protestant Reformation, nailed those 95 Theses to the door, and really people realized, oh, we can know God too. We don't have to go through the Pope. It renewed an interest in science and renewed an interest in discovering what is this creation that this God that can be known made for us. And really, these are areas that we've really, for the most part, nailed down up to about 1900. We'd already nailed these down. So these are areas that we don't have a lot of questions about. We know how mechanics works, the study of motion. Thermodynamics, the study of heat and thermal energy, sound of light, though there are some things we still don't understand about, like electromagnetism. These are things that really, up to about 1900, about that time, we had these areas nailed down. This is going to be the fivefold focus of this class, areas that we know really well. But a lot of the advancements we enjoy now are as a result of studying what's called modern physics. Modern physics rolled around refers to those things that have been studied in the last 100-ish, 120-ish now years. Things like quantum mechanics, particle physics, relativity. These are things we're not going to go into in great depth. We'll touch on a few of these things in this class, but a lot of it's very theoretical at this point. It's speculated, okay, this must be true based on what we know now. The problem is they've kept changing it. What they know now keeps changing because they keep discovering new things. So really, frankly, a lot of what I would teach you would be obsolete very likely within 5 to 10 years. But if you went into engineering, went into science, those sorts of things, in college, these are things you'd study in more depth because these are on the breakthrough edge of where we're making advancements in technology. So very useful, just not what we're going to focus on in this class. There is a chapter 27 at the very end of your books, and we will not have time to get that far this year, begins to delve into some of the things that, at least as of about 10 years ago when the book was written, were believed. How much of that is still accepted, I really can't say for sure. We're going to stay focused primarily on the classical physics, though, for this class. So, let's get into a little bit of science here. All right, let's talk about the scientific method. Every science class here at Grace Christian School seems to begin with talking about the scientific method. We're going to look at it from a little bit different approach here. We're going to look at the scientific method by breaking it into really 3 broad categories, 3 ways to answer scientific questions. And they're going to kind of encompass the things we see up here, right, on the board. But we're going to, like I say, break it a little bit differently. One way to answer scientific questions is the way that the old philosophers did it. They sat there and they thought about it. And they came to conclusions based on their own deep thinking. We call this cogitation. It's a great word. Sounds like you need to spit or something, but cogitation. Cogitation just refers to thinking, deep thinking. Based on your own experiences, based on your own knowledge, based on your own reason, I think this is probably what goes on. So cogitation, it's a great place to start. It's a lousy place to end, and that was where the philosophers made some critical errors, right? But at least they got the ball rolling, if you will. Cogitation is that level of the scientific method where you start with a question, right? Scientific method has to start by asking a question. I wonder why this? Or would this happen because of that? Is this the reason for that? Right? You're asking a question. Usually at the cogitation level, you'd come up with a hypothesis. I think this. For instance, if Michael and Kendall both jumped off the top of a building at the same time, well, Michael's considerably larger than Kendall. That doesn't mean Michael's necessarily large. It just means Kendall's that small. But I think because he's bigger, he's going to go splat before she goes splat. And so that might be the hypothesis. I had this question, I wonder who would go splat first. And I don't know how Audrey gets off the hook by being in the middle. But anyway, but you pose the question, you come up with a hypothesis, I think this, and then maybe, too, at this level of thinking, I would say this cogitation level should involve some research as well. And that's something that isn't always emphasized in the scientific method, but let's be real, a lot of scientific questions have already been answered. We don't need to go through re-answering, reinventing the wheel, as it will. So I would say the question is part of cogitation. The hypothesis, your best guess based on your own knowledge, reasoning, whatever, and then research. Has someone already answered this? Have we already figured this out? Because if we have, I don't want to do more work than I have to. All right? I'm willing to do the work, but let's see if it's already been answered. You could put for research, you could say, Google it. Okay? Google doesn't have all the answers, but it's got a lot of them. All right? Now, with cogitation, I think how it works hand in hand with cogitation is the next level, if you will, in scientific advancement. That's observation. Very likely observation has already been done for you to even come up with a question. For instance, maybe you notice in the fall time an acorn falls from the ground, falls from a tree, and a leaf falls from a tree. And the acorn hits the ground, and the leaf hits much later. And you're like, acorn weighs more than leaf. Acorn goes plop before leaf goes. You don't actually hear it. So I think because acorn's heavier, it hits ground first. So Michael's heavier, Michael hits ground first. We're not actually going to, for the record, we are not actually going to do this experiment. Okay, nobody's going to die, nobody's injured here, okay? It's purely theoretical. All right, but observation, it's also good, right? Probably your hypothesis is based on observation, right? And perhaps continued observation would be in order, right? Maybe you continue to observe things as you go around. Maybe you notice paper falls off Kendall's desk and a highlighter falls off Audrey's desk, and the paper took a while to hit the ground, but the highlighter went down right away. You're continuing to observe. But if we stop here, and again, this is where, in many cases, the ancient philosophers stopped too early, you can't really know, right? And this is where we got into STEM projects in 7th through 10th grade. You won't have to do a STEM project for this class, okay? But the third level is really where it becomes scientific, and that's experimentation. Experimentation. This is required for it to be truly scientific. The experimentation. And this is what we tried to emphasize as you did the STEM project, right? Had to be carefully designed, right? Ms. Morse worked with you extensively on that. Carefully design the project. Make sure you have a control. Make sure you have just one variable so that if results are different, we know what we can blame it on. Keep everything else the same. Do it over and over and over and over again, right? You can't just do it 3 times and be like, all right, I have conclusive evidence. No, got to do it a bunch of times if you're going to call it conclusive. But repeated many times. And throughout the experimentation, it's important that you keep track of some data. Right? It must have measurement involved, whether it be time, whether it be mass, whether it be distances or lengths, or maybe even a quantified measurement, but there has to be some level of measurement, some level of numerical data. You don't have to copy this quote by Lord Kelvin, but I want you to see it. One of the great scientists and mathematicians, because frankly the two really go hand in hand, he said, when you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you can't express it in numbers, your knowledge is of a meager and unsatisfactory kind. Until you can put numbers to it, you really don't know what you're talking about. We've got to have some level of numbers, some level of measurement in order to back up any sort of discovery here. So, keeping track of data as we conduct experiments, very important. With the data, obviously, we'd want to share those results as well. So once we've got the data and we've analyzed this data, we now know, okay, based on the data, this is what's true. Then we want to share those results. So maybe instead of just stopping at our observations of leaves and acorns and papers and highlighters, maybe we go to the experimentation level and we say, well, if I did a Michael and Kendall experiment, I could only do that once. At least with their full masses. All right, so what I'll do instead is I'll try some different things. I'll take this book and I'll take a Jolly Rancher and I'll drop them. I'll take I might take 2 Jolly Ranchers, one to drop and one to eat. Anyway, not my Jolly Ranchers, they're hers. So anyway, maybe you try a bowling ball and a leaf. But you try different things and you begin to test over and over again with different objects, and you begin to discover Book and Jolly Rancher hit the ground at pretty much the same time. Well, Book weighs way more than Jolly Rancher. So maybe you try cinder block and marble like they show in the picture. And at the same time, cinder block bus or sidewalk bus. You try different things over and over again, and you try a piece of paper crumpled in ball, you try a piece of paper shaped like paper airplane, you drop those, and they weigh the same, but they hit at different times. And okay, so why would leaf hit after acorn? It's not weight. Why is it, class? Drag or air resistance, right? The air is able to uphold the paper, if you will, or the leaf, or the paper airplane, right? It's able to rest on the air, if you will. There's an upward force of air, and that doesn't really affect that which is more dense, that which is concentrated mass, right? Mass to surface area ratio, right? So that's what we conclude in our experimentation. Of course, that's already been done, so we could have Googled that. But if we're the first ones to break ground, we would share those results. And of course, as we share the results, we're sharing the data we had with it, right? It's not, we found it's really, we now believe it's this because of our numbers. You'd have to share the numbers, we'd have to share the results, but we've got to have units for the data. Units are important. For instance, if we have these senior citizens in here, it'd be like, do you know how old Michael really is? Like, he looks so young, youthful, and handsome, and he's really about 200 months. Oh, months, okay. You know, that changes things, right? Knowing what the units are. Or Kendall, we want to talk about how much Kendall weighs. She looks so little. She actually weighs about 1,500 ounces. All right? But again, it's important to report units, isn't it? Right? It makes a big difference, right? So units are important as we keep track of data. So let's talk a little bit about units of measurement. There's the next section in your notes. She has no eraser in here. YouTube, this is not my classroom. She has no eraser. I can't believe it. I will bring an eraser later. But units of measurement. And there are different systems of units, and some of these we talked about in your earlier math classes, in junior high, for instance, and used in geometry and things like that. But units of measurements. One of the systems of measurement has several different names. The most common name for this system of measurements is SI. It's the international system, but in French, because the French get to name everything apparently, Système International, so SI. We used to call this the metric system, because it's based on the meter, at least length is. Also referred to as the MKS system, meter kilogram second system. Pretty much everybody calls it SI. That's what we're going to call it as well. Okay, so SI refers to the metric system. It's the old name for the metric system. Another system of measurement that we use here is called the Us Customary System. Now, we used to refer to this as the English system. And in fact, that's probably what you learned when you were in elementary school, was the English system of measurement. It uses yards and feet and pounds and cups and things like that, right? It's the English system is what we called it. The problem is the English don't use that anymore. They came up with it. English came to America, Americans colonized, Americans got mad at England, we're now our own people. England decides they like the SI, they like the metric, and we are stubborn because we're Americans and we do our own thing. That's why everybody hates us. And we do our own thing, right? Because why would we change? And it works well for us, so why would we change? And so the English like, stop calling it English, we don't use it anymore. So now we call it the US Customary System, also sometimes called the FPS, for foot-pound second system. these are the two broad areas of measurement. There's a third system of measurement. I don't know that anybody really uses it anymore. CGS, centigram or centimeter, gram, second. Nobody uses that anymore. So really it's these big two. Primarily in science, everything's done SI. We will occasionally reference the US Customary System just so we can relate to what we do, right? Just so we're like, okay, this is what it would be in our terms. Like when we talk about speed, what units do we use to describe speed? Miles per hour. It's what we do. We're in the US. We're miles per hour. In cars, everyone travels kilometers per hour everywhere else in the world. But in science, it's meters per second. Well, we'll relate the two so we kind of get an idea of okay, 37 meters per second. What is that, okay? And we'll translate it into our terms periodically just so we know what we're talking about since we are here in the US of A. So as we look at the SI though, since this is what pretty much everything we do is going to be based on, let's talk about the SI. And there are some fundamental units of measurement. It's actually the three biggest are abbreviated here, MKS. For length, we use the meter. In science, everything in science, if it's a length, it's based on the meter. That's the fundamental SI unit of length. The fundamental SI unit of mass is the kilogram. Now you might be thinking, well, why not the gram? Grams are so small. Kilograms are easier to use. So kilogram is the standard, the fundamental SI unit for mass. And then for time, this is true even in the English system, it's all based on the second. And that's where you get your MKS from, the meter, kilogram, second system. Now there are some other fundamental units as well. If you're looking in your textbook at page 6. Page 6, you see some other fundamental quantities, fundamental units here. Length, as we said, measured in the meter, mass in the kilogram, time in the second. Electric current, we'll get to later on in the school year, measured in amperes. We just say amps here in the US because we're lazy. Temperature, Kelvin, though most of the world uses Celsius. And we'll use a lot of Celsius in this class. Amount of a substance, here's something from last year, moles. You remember mole? Anyone remember the number for mole, Avogadro's number? Oh, Miss Morse would be so disappointed. 6.022 times 10 to the 23rd. Anyway, I won't tell her. It's on YouTube now, though. But amount of a substance measured in moles. Luminous intensity, candela. I think candle power or something like that. We won't really get into that a whole lot. But candela for luminous intensity. So there's your fundamental SI units there. Now, what's interesting is what these things are based on. The meter, for instance. At one point, the meter was based on supposedly the distance from the equator to the North Pole, and they broke it down into what they assumed to be 10 million equal units, and that was the meter, and that's what it was supposed to be based on. And then they said, well, we're going to come up with a bar of metal that is exactly that length that we call the meter, and we'll just base everyone else's meters on this one. And so they had this scientific laboratory where they kept it and they could measure everything based on the meter, and they would make copies of that. They put them in other places around the world. So when they make your basic wooden meter stick, they just compare it to the nearest one. That's a meter, and you're good to go. The problem is, anytime you handle that instrument, damage could occur. And so they realized, well, that's a bad way to just define the meter. So like, well, we'll tell you what we'll do. We'll define the meter in terms of the speed of light, or how far light travels. So you see it there in your textbook right next to the picture there of the standard kilogram. But since 1983, it says meter has been defined as the distance light travels in 1/299,792,458th of a second. You don't have to know that definition. But basically, meters are now defined in terms of how far light can travel. That way you don't have to have a magic meter made of metal in a certain laboratory somewhere. So they got away from that. Time is defined as the second, and they used to say, well, if we take the average solar day and we break it into 86,400 different parts, that's a second. But then average solar day, well, you know this, depending on where you live, days are longer or shorter, right? The closer you are, so maybe at the equator, and it's like, well, let's break it down differently. So you've heard of an atomic clock, right? Okay, a lot of what are called atomic clocks, if they're little bitty and they hang on your wall, they're probably not atomic, they're probably radio controlled. But they're based on an atomic clock, and they use that to, radio tower to control the other clocks. That's what most of our clocks in here are. It says atomic clock on that clock, in fact. But it's radio controlled, okay? But based on an atomic clock, and they now have defined the second, there at the bottom of the first column, as the amount of time required for 9,192,631,770 vibrations of a cesium-133 atom. So every time, for every 9,100,000,000, however many, vibrations, that's a second, okay? And the atomic clock is designed to count vibrations and sync off of that. And they've got small models now that only weigh about, again, this book is 10 years old, so they may have smaller models still, but as of the writing of the book, they had models that weighed only 65 pounds. Okay, so atomic clocks, whatever, but at least they had something a little more concrete, something physical they could look to. For the longest time, the kilogram was kind of what do you do? So they had an exact kilogram. It was supposed to originally be 1,000 cubic centimeters of pure water, a liter of pure water, at exactly 4 degrees Celsius. That was a kilogram. But liters of water is kind of awkward. So they made, in Paris, a platinum iridium alloy, and they made exactly a kilogram, called it Le Grand Kilo. They made copies, put them in all the other laboratories around the country, and if you wanted a set of masses, you would base your kilogram off of that one. But you better never touch it, because you could get oil on it, and that would affect the mass, right? And for years, for hundreds of years, they actually used it. In fact, for 130 years, they used Le Grand Kilo in Paris, and you see the picture of it there. That's standard kilogram, kept in a vault, untouched by human hands. And they discovered, though, just in the last 4 or 5 years, that Le Grand Kilo was losing mass. And in fact, it had lost about 50 micrograms. Now, that's 50 millionths of a gram. That was nothing, really. But the point is, it wasn't a perfect kilogram anymore. So how can you have this as your standard if it's not perfect? Well, they finally came up with a way of defining a kilogram apart from a physical quantity. And this is obviously after the book was published. So your book doesn't have this information in there. I'm not going to have you copy it down because really, it's hard to describe. They came up with what's called a Kibble balance, and they were able to find the exact value of Planck's constant. We'll talk about it later when we talk about light. Using Planck's constant, though, they could come up with exact amounts of energy in electromagnetic current. And they found this exact amount of electromagnetic force. If you use this exact amount of electromagnetic force, it can lift exactly a kilogram. So by use of this new technology and a perfect or more perfect definition or a calculation, if you will, of Planck's constant, they now have the kilogram redefined. There's just not an easy definition for it. So just know it's based on electromagnetic force. Okay, it's based on electromagnetic force, and that's about as far as we'll get with that. But that's actually just in the last thing, 2018. They finally had perfected that value of Planck's constant. We're able to now define it independently of Le Grand Kilo. So he's out of business. Anyway, so those are our major units, right? The meter, the kilogram, the second. These are our fundamental units of these three things. Again, we talked about moles and candela and amperes and kelvins and all those things. But with these, right, if we're trying to measure certain things, meters aren't always the best, right? If we're trying to measure the distance from here to Atlanta, describing that in terms of meters isn't particularly practical, right? Or how long the school day is. It's easier to say 7 hours, right? Though that's a US unit, US customary unit. But even in seconds, like it'd be so many seconds, it'd be ridiculous, right? Or if we tried to measure mass and maybe we're trying to measure a paperclip. Well, now the kilogram's not particularly effective. There are other units that we can use. So what we have now are what are called derived units. I'm running out of board space. But derived units. Derived units are units that are based on your fundamentals, your meter, your kilogram, your second, but we derive them. For instance, we even do this with a yard, right? What is a yard? Well, it's 3 feet, right? A yard is derived from the foot. Well, we can derive off of, for instance, the meter. For instance, you know this from your junior high math days. If you have 10 meters, you have a decameter. We derive a decameter from the meter by taking a certain number of meters. Or if you cut a meter into 100 pieces, you have centimeters. There you go. Okay, so hey, first day of school, we're remembering some things here. Basically, we're going to use metric prefixes. Some of these you already know. Some of them will be new to you, but we just use metric prefixes for our derived units. Now, if you look at the bottom of page 6, you recognize a lot of these already. In fact, you remember King Henry died unexpectedly drinking chocolate milk, or however you learned it. We have kilo, hecto, deca, unit, deci, centi, milli. We don't use all of those in science on a general basis. Some of these are used in math, not really used in science a whole lot. The ones with the asterisks there on page 6 at the bottom are the ones that are used most commonly in science. Now, mega is notated with a capital M. Mega means millions. Think of the lottery, mega millions. Don't play the lottery, okay? Bible teaches gambling's wrong, but mega refers to millions. So if you have 1,000,000 seconds, you have a megasecond. It means 1,000,000. The problem is we don't like to write 1,000,000 because that's really big, right? We'll use scientific notation. Well, in scientific notation, that's 1 times 10 to the 6th. Well, you might recall I taught you another way of showing scientific notation, and some calculators will use this as well. Instead of saying times 10 to the 6th, we'll use a short capital E, 6. So I refer to these as your E values, your powers of 10. But E6, that's the power of 10 associated with mega, E6. Kilo, you're already familiar with. You know that kilo means there's 1,000 of them, so a kilogram's 1,000 grams. Well, 1,000 is E3. And we'll use kilo quite a bit. Hecto really isn't used in science. Deca not used in science. Deci not used in science. The next one's going to be used in science is centi, represented with the lowercase c. Centi refers to a hundredth of something, right? 100th of a meter. Well, that's going to be E -2. So for instance, if you had a centimeter, well, that centi refers to E -2, or 1 times 10 to the -2nd. Milli is used for smaller quantities in science. That's an E -3. For instance, millimeters, lowercase mm. So notice mega is the capital M because it's big. Milli is the little m because it's small. So notice we have thousands, thousandths. We don't really do hundreds, but we do hundredths. We do millions. We also have millionths. Mega is millions. Micro. And I might be writing down too low for you to see. Is that too low to see? It looks like it. Let me write it up higher. Micro refers to millionths. And that's going to be E -6. Okay? So E6 is millions. E -6 is millionths. Here's the problem. We use the capital M for mega. We use the little m for milli. We're out of m's. So we're going to go with the Greek letter M. It's called mu, spelled M-U, mu, but it looks like a U with a hook on the front of it. Or, if you look at it slanty, it looks like a scripty M. So you can kind of see the M and the U at the same time in it, if that helps you remember how to draw it. But micro, so for instance, a microgram. Remember I mentioned a few minutes ago, Le Grand Kilo has lost about 50 micrograms. What's 50 millionths of a gram? So micro is E -6. And if we want to get down to really, really small values, for instance, remember a vibration of a cesium atom takes about a 9 billionth of a second, right? Because it takes about 9 billion vibrations to make a second. So if we go have millionths, E -6, billionths is going to be E -9, that's nano. And we'll just use the lowercase n for that. So nanoseconds, E -9, that's billionths. Now, if you wanted to go further, the book doesn't, so you don't have to know this. If you want to go down to trillionths, you might have heard of picoseconds. That's a trillionth of a second. That'd be E -12. You don't have to know that one. But we've got these different metric prefixes. These ones that you see marked with the asterisks are the ones that you need to know. Mega, kilo, centi, milli, micro, nano. You need to know 3 things. and it's the first 3 columns on this table. So if you'll circle those first 3 columns or highlight those first 3 columns, you need to know what the symbol is, you need to know how it's pronounced, and you need to know the E value, or the power of 10. Okay, I'm too lazy to write times 10 to the 6, so I do E6. But you need to know those E values, or the powers of 10, for the asterisked prefixes here. And that's how we'll get our derived units. Rather than, okay, there's 2 cups in a pint, and there's 2 pints in a quart. It's just all based on liters, for instance. If you're holding a quantity of substance in capacity there, you can measure it in liters, for instance. That's a metric unit. So you could have kiloliters, centiliters, nanoliters, megaliters, whatever. It's all just based on liters. We use prefixes to derive our values. Questions on what we talked about today? All right, so your homework for this evening, you're going to copy those 3 columns that you highlighted, just the ones that are asterisked, and you're going to copy the table at the top of the page. That's your written homework. So homework for this evening, read pages 2 to 9. Read pages 2 through 9. That's what we covered today and what we're going to be covering tomorrow. Read pages 2 through 9. And copy page 6, table 1.1, and table 1.2, asterisked first 3 columns. Copy table 1.1 and copy table 1.2, but just the first 3 columns and just the asterisked ones on those first 3 columns of table 1.2. We'll have a quiz over these things on Wednesday, so our lesson number 3. We'll take our first quiz of the year, and this will be kind of the focus, is knowing those things. Maybe some other terms as well, but that'll be a big focus. Any questions at all on our introduction to physics today? All right, with the bell rings, to be dismissed. Have a wonderful rest of your day, and I will get an eraser for tomorrow.